So, hello, let's get started. Today, we're going to continue chapter 5, which is all about conservation of energy. So far, I introduced the idea of work, where work is change in kinetic energy, is at its simplest form, is the best way to think of it, and how at any given situation we have two types of energy. If we're only looking at mechanical energy, there's kinetic energy and potential energy. Well, kinetic energy is the energy of movement, that when something is moving, its energy is 1/2 mv squared, and potential energy is the energy of location. There's multiple types of potential energy, but so far we've talked about potential energy to gravity, that if I lift something up, I give it potential energy that can become kinetic. And if you have only conservative forces, energy is conserved. Now, before I get further in this, I want to real quick make an announcement. I said this in an email, but I'm saying it again now. The office hours today from 3 to 4:50 have been shifted to 4 to 4:50. And by shifted, I mean shortened. There's no homework due tonight being the 10th, so I'm hoping this would be okay. If you wanted to meet between 3 and 4, send me an email. I'll find some other time I can meet with you. I have a meeting that they put at an awkward time. But otherwise, I introduced the idea of conservation of energy, and then I introduced kinetic energy and potential energy, but I've yet to do a problem. So we're going to jump right in with an example problem. And my example problem is about ski jumping. An Olympic ski jump has a height of 120 meters. Assuming no friction, how fast is a jumper going when they go off the end of the ramp? Now, this is the size of the ski jump. I'm saying from the bottom to this top bit, that's the 120 meters. If I'm going to do conservation of energy, I need to find an equation for the energy at each spot. Not like a value for the energy at each spot. I would never really bother solving for that, but an equation for the energy at each spot. Now, so far we only have two types of energy, kinetic and potential energy due to gravity. And so let's start with that potential energy. If I'm going to use potential energy to gravity, I have to define where the 0 point is. Where the 0 point should be, can be wherever the hell I want. I'm going to use the bottom of the ramp as my 0. And I'm going to say right where this bottom horizontal line is, that's my 0. That's the bottom. It makes life easy. I can then go and say, let's make an equation for the energy at all points. See, what I would do is I would say, nothing popped up. Okay, that was weird. I would say that the energy will always be kinetic plus potential. Now, I don't say this in the problem, and I keep meaning to change the wording here, so I'm going to make a mark to do it. I don't say how fast they go flying off the end, but let's assume they start at rest. Let's assume they just kind of pew over the edge and start with no initial velocity. If they start with no initial velocity, that means their energy at the top would be potential. They'd have potential energy because they're at the top of a ski jump. And if they just kind of go geek over the edge, they'll have no kinetic energy. At the bottom, they're at the bottom. That means at the bottom, their height is 0. And if their height is 0, they have no potential energy, but they're moving pretty quickly normally. And so at the bottom, they have kinetic energy. And conservation of energy says the energy at the top equals the energy at the bottom. And so I'll say the energy at the top, mgh. The energy at the bottom, 1/2 mv squared. And I'll set them equal. Now, there's a lot of m's here, but nowhere did I give a value for m. But that's okay, because there's a lot of them. I can divide both sides by m and they cancel out. And I'll find that in this case, gh equals 1/2 v squared. Now, if I want to solve for v, I'll multiply both sides by 2 and then square root both sides. And with some plugging in of numbers, I can solve for v. And I'll get how fast they leave the end of the ramp. Should be a dot here for sig figs. I'll fix that. Now, this is special to this problem. This won't be all problems in general. But that's the idea. I just said, what's the energy at the top? What's the energy at the bottom? Set them equal to each other. That's the idea for conservation of energy. Interesting thing about this, that speed, 48.5 meters per second, that's about 108 miles per hour, which is batshit crazy to be going wearing nothing but SpeedX and a Oh, speedex. Spandex. I meant to say spandex. Wearing nothing but spandex with big blades attached to your feet. In real life, they only really hit 100. They only hit 70 miles per hour. That's because there is air resistance and friction, so energy isn't fully conserved. Though I would go on a limb and say 70 miles per hour is still batshit crazy to go flying through the air in nothing but spandex and a helmet. There is one problem with conservation of energy like this, though, and that's velocity is a vector. I said the velocity is 48 meters per second, but really the velocity should include a direction. When you use conservation of energy to get velocity, it will not give you the direction. It'll just tell you the magnitude. If you want to find the direction, you need to go and just look at the situation and say, hey, look, which way are they going off the ramp? And use that to solve for the direction. So the whatever direction they're going off the ramp, that's the direction. This will always give the magnitude of the velocity. Questions? Okay, so you lift something up, you give it potential energy. You let go, it falls, it gains kinetic. That's what we were talking about. There's other ways to give something potential energy. See, if I want to make this guy move, lifting him up and dropping him, that works pretty well. But this is that elastical monkey thing I keep using. If I go and pull back like this and stretch, I can give him kinetic energy that way too, launching him forward, which even landed facing the camera. Springs can also give potential energy. But to understand potential energy for a spring, we have to first cover something called Hooke's law. Hooke's law is the force on a spring. And what Hooke's law says is that anytime you attach a mass to a spring, anytime you have a spring and you pull the spring, not a mass, or compress a spring, the spring will apply a force. And Hooke's law says that the force equals negative kx. That F of S is the force of the spring. I very seldom will put a sub S there. I'll normally just say F because it's easier and good enough. Negative sign I'll come back to. K is something called the spring constant, also sometimes called the force constant, though I normally use spring constant. The spring constant of a spring is just how stretchy it is, how well it can bounce. And X is how far it's been stretched or compressed. That if you can stretch the spring out more, the force is bigger, and so on. Now, the negative sign is to represent that X is always in the opposite direction of F. That if I have a spring, if I pull it down, the force is up. If I push it up, the force is down. It's always opposing the movement. And so right here, I have two springs, each one hanging the same mass. If I was to look at these springs hanging, what I could say is free body diagram is mg is pulling down on my springs. And they're being held up by the force of the spring. Now, both of these springs have the exact same mass hanging, but you can see as they stretch a different amount. They stretch a different amount because they have different spring constants. The different spring constants lead to different amounts of springiness. This is the wrong video. I don't want the one where they're bouncing. That's, sorry. Wrong video. You know what? Do I do the not bouncing? No. Bouncing is later on in the semester. For now, I'm just going to leave it paused. I don't feel like finding the video right now. And so I can say that a spring, anytime compressed or pulled, would give a value. I did not actually give you the units for K. Anyone in the room want to say, what's the units for K have to be? I'm not going to bother opening a poll for this. Well, I can use dimensional analysis. If I take my equation, I drop the negative sign because the negative sign is just direction. I'm just saying magnitudes here. If I take this equation, divide both sides by x, I get that K is the force of the spring over how far it's stretched. But force is in newtons and x is in meters. So K will always be in newtons per meter. Now, what I want to talk about this chapter isn't the force on a spring. I just wanted to cover it real fast, but the potential energy. You see, if I want to make something go flying, go get that monkey back. When I pull his arms, when I take this and stretch it out like that, that's getting ready to fly forward. And see, what that's doing is that's giving a potential energy, an energy waiting to become kinetic. And just like gravitational potential energy, it's just an energy that wants to do something else. The potential energy of any spring is 1/2 kx squared, where k is the same spring constant, and x is once again how far you pull it from not stretched. So this would be a little bit of potential energy because I pulled him a little bit. This would be a lot more potential energy because I pulled it a lot further. And in fact, that you can give something potential energy by a spring, and you can solve for exactly how fast it'll fly because of that potential energy. Now, when I shoot this monkey in the air like this, I'm arcing him through the air, which means I'm giving it. I have a better demo of potential energy, but I'm waiting to do it on purpose. Today, by the way, is normally the most fun class we have in person because the thing I'm about to use for a demo, and then I make a fool of myself in class, so it sucks you're getting it online, so I apologize. If I go and launch this guy up, what I'm going to do is I'm giving him potential energy due to a spring. But if he flies upwards, that means he gets gravitational potential energy too. In a problem that includes gravity and a spring, you have to include all the terms. But we can still use conservation of energy. If this spring-loaded gun launches a ball up in the air, I can say it initially has spring potential energy. Right when it launches, it'll have kinetic energy. But as it goes up in the air, the kinetic energy will go down as the potential energy goes up. But at all points, the total energy, or total mechanical energy is what that TME is supposed to stand for. But the total energy will be constant. This is the basis of anything you launch by a spring, including my Nerf gun. So, I got this Nerf gun. Fun fact, if we were in person, I would have had to contact campus safety to do this demo, so that's a fun thing. This gun, what it does, has a big spring right here. When I pull this back, what happens is I'm compressing that spring. When I compress that spring, what happens is I'm giving a spring potential energy. And I'm just going to bring that forward again. The spring is still compressed though. And that what is because I took the spring inside and compressed it, there's now a potential energy, the potential energy of 1/2 kx squared. Well, k is going to be how stretchy that spring is, and you can see pictures of other Nerf guns below to see how it looks. This one is most similar to the one in the bottom right. I don't have the actual one, though I have opened this one up before, but I don't have a picture of it. And x is how far it's stretched. In this case, how far it's stretched was that far, the distance from there to there. That's how far I compressed it. And so that'll say how much potential energy I get. If I then go and fire this, what happens is all of that potential energy becomes kinetic. That I'm taking the potential energy due to a spring, I'm loading it up, I'm getting it ready to go. And when I let go of the spring, let the spring undo, that was a dud. That potential energy will become the kinetic. The dart will go flying forward. In fact, I can figure out exactly how fast the dart leaves the gun. Because if I'm not changing height, and I'm firing this pretty flat, I can figure its velocity right here as it leaves. Its velocity will change as it goes further, because if you watch while I fire this, it's hitting that pillow at a lower height. It's arcing downwards. That means it's changing gravitational potential energy. But right when it leaves and it hasn't changed height yet, I can talk about the energy. I can say that when I cock this backwards, I give it a certain amount of potential energy. That potential energy being 1/2 kx squared. How far it cocked, and how springy the spring inside here is. When it fires, the spring uncompresses, and all of that becomes kinetic. No, good thing my cat isn't up here. I'd be Taro chasing everything. And so that can say how fast the dart's going. Well, the kinetic energy of the dart will be 1/2 mv squared. And conservation of energy just says that the energy initial equals the energy final.
Excuse me, I have a question.
Yes.
So The first equation on the left, the potential energy, that's the initial, like you loading the spring.
Yep, that's me
And
loading the
then
spring.
then the kinetic energy is you pulling the trigger and it releasing.
Yep.
Okay. All right. Thank you. Just want to check on that.
Nope. And conservation of energy, once again, says the initial energy equals the final energy. And so I can say that final energy was 1/2 mv squared. That initial energy was 1/2 kx squared. And you can actually solve for exactly how fast, I forgot what I solved for here. I could solve for exactly how fast the dart leaves the gun. Because I can just set them equal. And if I multiply both sides by 2, divide both sides by m, and square root, I'll get the muzzle velocity. There is actually like a community of people online who mod Nerf guns. And how they mod ones like this, because there's also ones that use air instead and pressure, which is a whole other can of worms. But how they mod ones for springs is they just replace the spring with a much bigger one. If you make a much more powerful spring, it will shoot further faster. This also, and this, if we were in person, we'd be in the pit, which gives me a lot more room to shoot around. This gets a lot more complicated if I shoot it up. Because if I shoot this thing straight up, try that again. If I shoot this thing straight up, what I can say is that as it goes upwards, it's not only getting kinetic energy, but as it leaves, it's changing height. If it's changing height, I also have to include gravitational potential energy. And that my energy change will be both or my potential energy change would be both kinetic, try it one more time. My potential energy change would be both gravitational and spring, making it a lot more complicated. Questions though before I do a problem? Okay. So since so far my demo today has been a toy from my childhood, at least I'm claiming that. I think I got that in like grad school, but that's another story. Let's talk about other legit toys from my childhood, or at least my sister's. And I want to talk about something that would have been done in person if we were in person, but I have a very, very, very old pogo stick. And you know what? Just for a second, I'm going to share a sound so you can hear how great and old this thing is. It is squeaky as fuck because it's ancient. It is older than probably any of you because it's my older sister's. I think it's older than me, actually. Let's say I got a pogo stick. What a pogo stick is, really, is just a big ass spring. And that if I go and step on a pogo stick, what I'm doing is I'm compressing a spring. And if I get on the pogo stick and start bouncing, sorry, I should really make it so you can hear the audio, but it would just black me out, but it's just so much squeaking. If I go and jump on the pogo stick, what I'm doing is I'm taking a spring, giving potential energy. That potential energy is turning into kinetic energy, but is also dealing with gravitational potential energy since I'm going up into the air. Only the best pauses for this class. So let's say the pogo stick has a spring constant of 2.5 times 10 to the 4th newtons per meter. And I'm going to talk about 3 different locations. I'm going to talk about when I'm all the way down as low as I can get. I want to say at that point, I am 0.1 meters beneath my 0 point, which just matches the picture to the right. That's when it's compressed all the way. At that point, I'm 10 centimeters down. And I'm momentarily at rest. Because if I'm in between bouncing, we know velocity is 0 and you're in between going up and going down. Well, if I'm in between going down and going up, my velocity is still 0. And I want to talk about 2 other locations. Right when I'm here, still touching the ground but flying upwards. That if this was when I was actually jumping, I would be on my way up. And then that's going to be called point B. And at that point, I'm going to say its height is 0. I'm going to define my 0 as there. And I'm going to come back to that in a second. And I'm going to then go flying up in the air till I hit a maximum height. At my maximum height, that's my maximum height. At that point, I'm in between going up and going down. So at that point, my velocity is 0 again. Given my, it says weight, given my mass, it doesn't even say weight spelled correctly. Given my way, that should be mass. I'll fix that in a second. You know what? I'll just fix it real fast. So if I have a mass of 90 kilograms, which is a joke, I'm much fatter than that, I can use this to find my velocity at point B and the maximum height at point C. Now I did something weird here. For gravitational potential energy, I like to define my lowest point as my zero. And so you would think that I would say my height is zero. Oops. My height is zero right here. But I instead define this as my height is zero. And there's a reason for that. In the spring equations, the 1/2 kx squared, or Hooke's law, kx, your height is not arbitrary where your zero is. You see, when I do gravitational potential energy, I can define zero height wherever I want. Here, 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 doesn't matter. But spring potential energy? For spring potential energy, your 0 point is the spring with nothing acting on it. This is 0. This has more potential energy. But 0 is always where it's relaxed. And going with my pogo stick idea, when I was, oops, this is so weird to do this without bouncing on a pogo stick. But right there, that's when the spring isn't stretched. How? Just like when I saw the video, that's just sitting on the ground. That's the spring not stretched, so that has to be the 0 for the spring. And since I'm going to talk about the position of a spring and the position of me, it's easier to make them the same units. And so wherever I define 0 potential energy due to spring, I'm going to make that 0 potential energy for height. So I can define everything the same. Make sense? So here's what I know. I know the spring constant of the spring. I know my mass. And I know at A, I'm 0.1 meter below my 0 point. And I said at B, I'm at my 0 point. I also know my velocity at A and C, that my velocity at A is 0, because when I'm in between going down and going up. And at C, my velocity is 0, because I'm in between going up and going down. That I'm talking about when I'm just actually on this thing bouncing, let me actually get on this thing bouncing, when I'm at my lowest point and my highest point, which obviously my highest point is not very high, because fat man on a child's pogo stick. Side note, I tried to get the school to buy me an adult pogo stick to teach this. Adult pogo sticks are very expensive for ones that can take my weight. And it was really, when I went and asked official people, hey, I need a pogo stick to teach, they all just looked at me funny, told me I was crazy, and to go away. They would not take me seriously. I don't know why. Anyways, I asked for two things. What's my velocity at B and what's my height at C? And I can solve this. What I'm going to do is I'm going to get rid of all the text. Just keep those notes. I can say at all points my energy is the same. That my energy, which is going to be kinetic energy plus potential energy, and in this case, I'm changing height and I got a spring. So I have both gravitational potential energy and spring potential energy. Because, hold on, put this back on. Because once again, I'm doing both. Yeah, the squeaking is. Seriously, I need to oil this thing. Stop. 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 There we go. But at all points, my energy is the same. And what I would do is I'm going to make an equation for the energy at each spot. I'm going to say at each spot, what is the kinetic? What is the gravitational potential? What is the spring potential? And I'll add them up. I'll say at A. And let me put up this figure along with the other figure. Can I get smaller? Cannot get smaller. Okay, whatever. I'll make this work. At A, this is A. At A, my velocity is 0 because I'm in between going down and going up. And so that means my kinetic is going to be 0 at A. But I have potential. I have potential. Make me feel good about myself. I have spring potential because the spring is compressed. And I have gravitational potential because I dropped downwards. Now note my height at A is negative, which means this number is going to be, my potential due to gravity is going to be negative in the end. But I'm leaving it as a positive value and I have the negative sign just for X. At B, I'm flying off the ground. At B, my height is 0. I'm still on the ground, but I'm right at my 0 height, but I'm traveling upwards. So at B, I have no potential. There goes that potential so quickly. See, at B, the only thing I'll have is kinetic energy because I'm moving, but I'm at the zero height. And then we have C. C is when I'm at my highest point. At my highest point, if I throw something up, right, at the highest point, your velocity is zero because you're in between going down and or going up and going down. And so my velocity at C must be zero. But I'm up high, so I have gravitational potential energy. But here's the interesting thing. I might have gravitational potential energy, but I don't still have spring potential energy. Because if you look at the bottom of my pogo stick, at A, right, this has a small little gap. You can see that the spring is compressed. Actually, it's stretched. I think the spring is in the actual neck. That there's only a little gap here because it's pushed down. When I get up to point C, the pogo stick isn't compressed. The spring's not doing anything. The spring's just going whee through the air. And so at C, I only have gravitational potential energy. And conservation of energy says the energy is the same at all three places. That the energy at A equals the energy at B equals the energy at C. Okay, questions there, because it's only going to get worse before it gets better. So, I wanted to find two things. My velocity at B and my height at C. Let's start with the velocity at B. What I can do is I can look at these equations, say, what do I know, what do I not know? And I can say, I know every single thing in A. Actually, let's undo that. I know everything in A. In B, I don't know the velocity at B. And in C, I don't know my height at C. And so if I want to find the velocity at B, I can say EB equals EC, but that's not going to help me. I have two unknowns. What I'm going to do is say EA equals EB. And if I set EA equal to EB, EA and EB, I can solve. I'll just say EB equals EA. I did the opposite order. Now if I want to find velocity at B, I did this in did both in one step, it looks like, so that was dumb. I can multiply both sides by 2. When I multiply both sides by 2, this will cancel out a half, and put a 2 in front here. And then I can divide both sides by m. When I divide both sides by m, it'll cancel out this m, and put a 1 over m over here. Sorry, I did both steps at once. And that can give you my velocity. I solve for the velocity squared first, just out of laziness. I can plug in my numbers. Keep in mind, x of a is a negative number because it's below the 0 point. And then I can square root to get the velocity. And what I'll find is my velocity should be about 0.9 meters per second at that point when I'm just leaving the ground. Oh, you know what? I just remembered how I taught this online last time. I wish I remembered this earlier. I have an old Happy Meal toy. And so I'm saying my A, my B, my C. Oh, that's Mario. Ah, Mario went flying. Sorry, I forgot about this guy too now. And so if I know how far I compressed at A, and I know how fast he's moving at B, right when he's leaving the ground, that at this point, that is the velocity. Okay. Now I also asked for the height at C. If I want the height at C, well, I now know everything in A and B. So if I want the height at C, I'm going to set the energy at C equal to either the energy at A or the energy at B. Now, looking at these, I'm going to set C equal to B because A looks complicated. There's a lot of shit in A, and B has only one term. So out of pure laziness and nothing else, I'm going to say my energy at B equals my energy at C. I can divide both sides by M, then divide both sides by G, and find how high I get. Well, if I plug in some numbers, I get the height. And I get that I go 4.17 centimeters off the ground. That this guy, when he compresses and shoots up, doesn't make it very far. And actually, if you look at my video, I don't think I even make it 4 centimeters off the ground. If I had to guess, I'd say I make it like 2 centimeters. To be fair, it's not very high, but I'm very fat, and it's a very old pogo stick. And no one wants to pay for a new one. They're like, we have a budgetary crisis. We can't buy pogo sticks. I think everyone's priorities are out of line. Pogo sticks are more important. Any questions? I just launched Mario.
So, Dr. Schweidenbach.
Yep.
Calculations for spring energies and such,
Mhm.
they work for all elastic materials that act like a spring, right?
Yes. Although elastics can get a little questionable in acting like a spring, but as long as their force can be approximated with Hooke's law, you can treat with the F equals negative kx, then yes, it works. So like this monkey that I was talking about with his elastic arms, I can treat him as one because this is close enough to acting spring-like. This should work for anything spring-like, but some more complicated things, like I mentioned, compressing air and using compressed air to launch something with other types of Nerf guns, that doesn't really work because it doesn't follow spring equations. But any other elastic, it should work. Okay, that's what, which is a pile of Nerf darts on my couch. That's what I was gonna say on energy, which I still got 20 minutes left. I got a bit more today, but that's what I want to say for energy for now. Be good so far with conservation of energy. When doing machinery, when using machines to actually make shit do something, people normally don't talk about the energy output. That energy is not a common term to use in the real world, because what people normally care about is the rate at which you do energy. And this is going to get to our last equation, our last the last important equation of the chapter, and that is power. Power, by definition, is the rate energy transfer takes place. Power is change in energy over time. Now, keep in mind, change in energy, for mechanical energy at least, is work. We're going to have different versions of change in energy for thermal energy when we get there. But for mechanical energy, change in energy is work. And so power is, by definition, work over time, or at least average power. Really, there should be a bit more complication going on here involving involving derivatives, calc-based, meh. But on average, when you talk about the power output of an engine, you're just talking about how much energy it can apply in a time period. Power uses the units of watts, where a watt is a joule per second. The American unit for power, which is commonly used in some things and not others, like people also work in watts in America, like a light bulb has how many watts, that's its energy output in a time period. But also horsepower is power. Horsepower was first defined by James Watt, which is pretty fun that the unit is named after someone who defined a different unit. I kind of like that fact. He's like, guys, I made this unit. People are like, cool, we made a different one. We named it after you. And he's like, but I made this one. Um, the reason a horsepower exists is James Watt made one of the first steam engines, and he was trying to market it, and he was trying to say that his engine did as much work as like 3 horses. So he said it had 3 horsepower because this one thing was as good as 3 horses. That's the basis of a horsepower. 1 horsepower, though, is 746 watts. If you talk about the horsepower of an engine, you're just saying it's power. You're saying how much energy it can put out in a time period. Okay. I'm going to do a very complicated example problem here about this, but it's kind of an interesting one. This problem is admittedly out of date. This is a 2016 thing that really I should rewrite this problem, but I can't imagine it changed so much in the time period, but maybe I'll look it up sometime. But a 2016 Ferrari 488 GTB weighs 3,360 pounds. And they say the engine is 660 horsepower. Let's say the engine is perfectly efficient, that the engine only creates movement. How long would it take the Ferrari to go from 0 to 60? See, if I want to solve for this, what I can do is I got to start with unit conversions. And here's some conversion factors just so I have them. If I'm going to say how long it takes the car to go from 0 to 60, I'm saying how long does it take it to go from 0 meters per second to 60 miles per hour, which can be converted. 1 mile is 1,609 meters. 1 hour is 3,600 seconds. And so 60 miles per hour is 26.82 meters per second. I then say this has a horsepower of 660. Converting that, that means it puts out 492,000 watts. And I don't care what the weight is, I want the mass. So I'm going to put these numbers at the top. And what I can say is power is work over time. But work, as we talked about before, is change in kinetic energy. That work is final kinetic energy minus initial kinetic energy. And if I'm going from 0 to 46.82 meters per second, that 0 means my initial is 0. So in this case, work is just the final kinetic energy. And so the power is 1/2 mv squared over t. It really bothered me to put a fraction within a fraction. This is the same as that. I just wrote it differently because I don't like having fractions within fractions. But I want to solve for time. If I'm going to solve for time, I will multiply both sides by t, divide both sides by p. And by plugging in my values, I can get that it takes 1.1 seconds. Now, this call does not go 0 to 60 in 1.1 seconds. It takes it 3 seconds. You see, this is making an assumption, and that's the car is perfectly efficient. No engine is perfectly efficient. When you have, especially a gasoline-based engine, some of the energy is going to go is wasted to heat. The car heats up. That's a different type of energy. Also, some of the energy is going to go to lighting the dash. Some is going to go to playing the radio. But the bigger issue is some is going to be lost to heat. No engine is perfectly efficient. And really, conservation of energy is always mildly broken. My pogo stick problem, energy wasn't conserved. I know energy wasn't, theoretically energy should be conserved, but I know energy wasn't really conserved because that obnoxious noise proves that energy wasn't conserved. We're going to assume conservation of mechanical energy in most of these problems. But mechanical energy is not always all conserved. However, total energy is. If you have non-conservative forces, aka the engine in a car or the squeaks of my pogo stick, you can still do conservation of energy as long as you include all energies. That mechanical energy will not be consistent, but some of the energy will go to other things. And the work done by non-conservative forces will be that change in energy. And so that's why the car can't do it in 1 second. It needs 3 seconds, is because some of the energy becomes thermal energy. Some of it becomes electroluminescent energy. Some of it becomes electrical energy. In general, energy cannot be created or destroyed. The total energy of a system, will always be constant. I right here, if it doesn't remain constant, it must have crossed the boundary. That just means that if you look at something and you say, hey, look, energy is not conserved here, it means, no, it went somewhere else, you just missed it. It just can go to a lot of things. Calories in food, that's a type of internal potential energy. That energy can follow many forms. This chapter, we've only talked about mechanical energy. that when you push something or pull a spring or bring something up to drop it, energy of physical movement. But I want to at least touch on all the other types of energy. The other energies you have to deal with. There is thermal energy. This is energy as temperature. Kinetic energy is relates to how fast molecules are going. And change in thermal energy is heat. This would be the last 2 chapters of the class. There's also electrical energy. This is energy transfer by electric current. If you take Physics 2 with me next semester, you will cover that then. There's electromagnetic radiation, which is light waves. That is also in Physics 2. And that's the idea that when light is just a type of energy. That's why if you shine light on something, you can heat it up. There is chemical energy. This is the energy in chemical bonds. If you want to learn about that, take a chemistry class. I'm not going to talk about it at all in any of my classes because screw chemistry. Chemistry's dumb. Sorry, I really hate chemistry. It's a thing. It's actually an ongoing joke that most physicists don't like chemistry and most chemists don't like physicists. I don't know why it's an ongoing joke, but from my history, I see it's normally pretty true.
Yeah, I'm physics. Chemistry sucks.
Yeah, thank you. And the other type of energy that exists is nuclear energy, which is actually back to physics, but I'm not going to get to in any of my classes because we don't get to that level. But it's just the energy stored in the nucleus of an atom. But for now, we can just stick to mechanical energy with this chapter. And once again, we're going to use conservation of mechanical energy, how we can turn potential energy, be it from gravity or a spring, into movement. Okay, that is actually the end of the chapter. I'm ending 10 minutes early. The pogo stick thing goes a lot faster when I'm not falling on my ass in front of the classroom. And I don't end up jumping on a pogo stick while firing a Nerf gun in the air, because that happens sometimes. So I am going to end a little bit early. That is everything you need to do your next homework. Once again, today is the 10th. Yeah, today's the 10th. There was no homework due today on the 10th because I didn't cover a new chapter last week. Your homework is due next week on the 17th. There is still a lab due tomorrow on the 11th. I showed in my office hours today. And Friday we'll do practice problems where we'll be looking at conservation of energy. I do want to stress right now, we are not actually done with conservation of energy. We are going to revisit in chapter 8 with another type of kinetic energy. But for now, we're good until we hit that.
Oh, great.
It's okay. The last part is from things spinning. 7 and 8 is all about rotational physics. That part's fun. So, good luck with homework, I guess. I don't know why I said good luck. Whatever. I'll see you Friday. Bye.